Good morning, dear delegates and organizers. My name is Vasileios Vlachou, and I'm PhD student in the School of Electrical and Computer Engineering at the National Technical University of Athens. The today issue of the presentation is about energy saving in elevator by using a particular permanent magnet motor drive. Today we know that both electrification included in the first applications, as well as new hybrid and electrical motor as basic transportation vehicles are a very important research field with continuous challenges. It is therefore worth researching ways to achieve the highest possible rates of energy saving with the lowest energy consumption. Here, my main research interests are included as well as those of my co-authors. The basic aspects that will be analyzed in today's presentation are a general introduction to the driving systems, the control techniques, and the vector control in a permanent magnet synchronous motor that was studied in the application. As mentioned, above any motor drive involves the use of power electronics, which we will focus in the next chapter. It is also worth considering some basic parameters in a drive system that lead to lower current and power consumption compared to their nominal characteristic, and which can be modified at various time intervals and conditions to bring about change. The last part includes the results obtained on the basic issue of energy efficiency, the main conclusion drawn, as well as future proposal that could be area of research and study leading to higher rates of energy saving. In this slide, we see the diagram of the motion system. This must include the appropriate controller, where the main role in adapted to the requirements of the application, to the characteristic of the motor, and the inverter in order to create a suitable drive system. These are PI, PID current, speed, and the rotor position controller using encoder. There are several categories of electrical motor controls. The simplest in implementation with low cost, but which concern electric machines, and lower power in the open loop control. This type of control, because it has no feedback, creates stability problems in the system. Also, another category used in my research in the vector control with file oriented. On the right is shown the operating diagram of the system. With the type of control, there are no stability problems due to the current and speed controllers, but the main disadvantage is cost of construction. With the use of VVF technology were observed a significant advantage, not only in the energy part, but also in the lifetime of the electrical motor. This slide illustrates the control structure diagram of the arrangement using VVF. The basic parts of the VVF system used in elevator application are the rectifier, the inverter, and are controlled by the control unit. In the following, two pictures showing the voltage pulse produced by using a sinusoidal pulse with a modulation technique. The bottom left picture showing the modulation of pulses in the case of the half and nominal voltage and frequency, and the bottom right figure showing the corresponding modulation of the pulse in the case of the nominal voltage and frequency depending on the programming velocity and starting impetus. There are shown the motion curves of the elevator during ascent and descent. The specific speed curves are programming into the inverter to determine the movement of the system during elevator operation. Through this curve, and we can determine the maximum speed of the elevator and the time period during switches performs acceleration, constant speed, and deceleration motion. The basic equation in order to determine the energy savings in the drive system are calculated from the characteristic speed curve. The equation relates the area and energy consumption by the drive system's calculated friction, belt, and bearing losses. Two different types of elevators and electrical motor were used for my research. There are two electrical motors with the same efficiency, same number of poles, and approximately the same output power. The first electrical motor is a permanent magnet synchronous motor powered by inverter using VVF technique, and the other is an induction motor powered by network. The two tables show both the basic characteristics that were determined approximately in order to construct the dynamic model of the electrical machines and the technical characteristics of the two different chambers. The next 6 slides show the current consumed by the motor during the movement of the lift when it is accelerating, deceleration, and movement of constant speed. In the experiments, I used the chambers were loaded with empty load, with half their nominal load, and with a full load. Therefore, we observe different current consumption results during the ascent and descent of the motor. This is due to the existence of the gravity coefficients and the counterweight. The rated current of the electrical motor was calculated 20.14. However, as we can observe in the graph of the simulated current consumption versus time, is lower current consumption during ascent and descent with difference is due to, in the case of half payload, the weight of the chamber is approximately the same as the weight of the counterweight. So either during ascent and descent, the electrical motor has approximately the same load and the same consumption is both direction of motion. In the case of empty load, the counterweight is a higher weight than the empty load, so in the descent the electrical motor has to upload the counterweight and thus has a higher load, more power, and therefore higher consumption current. On the contrary, during the ascent with empty load, the counterweight descended with help of gravity, and electrical motor has lower load, power and consumption. Focusing of the case of energy saving and the total percentage achieved, two scenarios of electrical movement were obtained. In the first case, we had a higher number of poles, while in the second case, we had a lower number. In this slide, we're showing the energy consumption during the descent and the ascent. The slide shows the daily energy consumption for each case of the electrical motor. It is calculated at the sum of the number of calls received to each floor times the energy consumption resulting from the movement of the chamber from the ground floor to each floor. By summing up to the total energy consumption for each of the two cases studied, as well as the condensation with VVF and without VVF, we find that in the case with a larger number of calls, we had a higher percentage of energy savings. The basic conclusions is the modeling of the elevators system involving electrical motor system leads to more efficient study and analysis of their operation and motion. By using the VVF technique is driving the electrical motor, a higher percent of energy savings has been observed. The percent of energy saving achieved significantly depends on the loading condition of the elevator and on the number of holes considering. The case of full load is similar to the one of empty chamber is the response observed during movement. In the case of full load, the VVF system adapted offered a lower percentage of energy saving, while a higher percent of energy saving has been assessed under operating condition involving half of rated power. The active lifting force is responsible for consuming a large part of the specific energy. On the role of the counterweight, a lower weight value result in a smaller energy consumption in empty chamber conditions, but the higher consumption is fully loaded for the condition of the chamber. Finally, in addition, it is appropriate to mention some future investigation that can bring about higher rates of energy saving, as in the case with the use of regenerative mechanism. In the case of the electrical motor acts as a generator and results part of which energy to the grid. In this case, an addition DC-DC converter is used. With the mechanic we can achieve 50 to 60% energy saving rate of the system. The image below show the system of the lifts with its main parts. In addition, with proper maintenance of the system is required to minimize friction and vibration losses, and by using appropriate belts, greater losses and greater energy savings can be achieved. Thank you for your attention.
Thank you for your presentation. So, any questions from the audience? Yes?
Christos from Engineering of Technology.
Yes.
I would like to ask, first of all, these results, it's lab results or you tested in a real elevator?
Real elevator.
So, how you see it going on? I mean, because you mentioned something about energy saving, in this hotel you have 3 elevators, so how you see it to expand in more elevators tested and get more results in the near future? Expand your study, let's say.
Application in the real life.
Exactly. In the real life. I mean, if you go to this hotel and you say to them that I have this idea of getting more energy efficiency with your 3 elevators, so have you thought about it?
The VVF technology is a very important category of both elevator speed and the electrical motor vector control.
But it's possible to apply it to any other elevators, right? Is it possible to apply in any elevator?
Okay, now let's continue this discussion later. Any more questions? I have a question myself, actually. So, in the initial parts, you shown quite a high percentage of increase in efficiency, but it wasn't clear to me. Is this because you go for a vector drive, or you change the profile of the lift?
The VVF technology is a very important.
That was for the permanent magnet, right?
Yes.
So the main difference between the permanent magnets lift and
yes.
the induction was the VV309 drive.
Yes.
The profile remains the same.
Yes.
Okay, thank you.
Thank you.